Hello, I'm Christy Patton-Lukes. I'm a chemical engineering professor at Missouri S&T. This material in this video is tied to the course Intermediate Thermodynamics, and we will be looking at experimental observations in thermodynamics. Our goal here is that by the end of the lesson you should understand the observational background that is the basis of all thermodynamics. My source on this is Stanley Sandler's textbook, Chemical and Biochemical and Engineering Thermodynamics, which is the 5th edition I'm using. So we're just going to go through those. His first observation that he points out is that in any change of state, other than nuclear, we're not going to deal with those, total mass is conserved. Okay? We do know that nuclear reactions destroy mass, but that's a separate study. We will not be looking at that. So for our purposes, mass is conserved. Second, in any change of state, total momentum is also a conserved quantity. Third, in any change of state, the total energy, and this total energy includes internal energy, potential energy, kinetic energy, and then heat and work interactions between the system and the surroundings. The total energy is also a conserved property. The fourth is that a flow of heat and a flow of work are equivalent in that supplying a given amount of energy to a system in either of these forms can be made to result in the same increase in its internal energy. Heat and work, or we often will call these thermal energy and mechanical energy, are not equivalent in the sense that mechanical energy can be completely converted to thermal energy, but thermal energy can be only partially converted to mechanical energy in a cyclic process. And we'll be taking advantage of this when we start looking at these cycles and thermal efficiencies. Next, a system that is not subject to forced flows of mass or energy from its surroundings will evolve to a time-invariant state that is uniform or composed of uniform subsystems. And this is what we will call the equilibrium state. So if you do not have flow in or out, eventually over time things will reach this equilibrium state. Number 6, a system in equilibrium with its surroundings will never spontaneously revert to a non-equilibrium state. We frequently call this the definition of equilibrium. Equilibrium states that arise naturally are stable to small disturbances. So in the last lesson we looked at metastable, and the ones that arise naturally will not be that unstable, and metastable will be subject to change if you wait long enough. 8th, the stable equilibrium state of a system is completely characterized by values of only equilibrium properties, and not properties that describe the approach to equilibrium. So these equilibrium properties are a function of the state itself and that material. Now, second to this is that for a single component, single-phase system, the values of only 2 intensive, independent state variables are needed to fix the thermodynamic state of the equilibrium system completely. The further specification of 1 extensive variable fixes the size. Next, the interrelationships between the thermodynamic state variables for a fluid in equilibrium also are going to apply locally, so at any particular point in a fluid that isn't in equilibrium, provided that the internally reversible processes are rapid with respect to the rate at which changes are imposed on the system. This means that we can be looking at the macroscopic level and not have to worry about the details of the microscopic level to get an adequate description of our process. For the fluids of interest in this course, this condition will be satisfied. And our final one is that the flow of heat, which we designate Q, in joules per second or watts, so the rate that arises because of a temperature difference is linearly proportional to the magnitude of that temperature difference. From heat transfer, we know that we can designate this as either Q equals negative H delta T, or Q is negative K dt dz, whether we're talking about convection or conduction. So this completes our observations from experiments and everyday life. What we will be looking at next is how we can use the conservation properties to develop the first law, the material balance equations, and those things that become the key to solving so many problems. Thank you for listening.